norm testing. I just wanted to ask you all to, if you could, leave any questions you may have, leave them to the end of the presentation, because we will send out a recording of the full presentation after we've finished. We'll send out a link to that, and the recording also will become available on our website in a couple of days' time once we've uploaded it. So if you could leave your questions to the end. There are various ways you can ask a question. You can put up your hand on your little toolbar there on the side and raise a question, and then I'll answer them in order. Or you can type out a chat message and send that to me, and I can read that out at the end of the presentation. So I'm now going to hand you over to Amy.
Thanks, Tim. Hello, everyone. Today I'm giving a short presentation on norm analysis, and we'll have plenty of time to answer questions at the end. So laboratory analysis for norm, we're going to talk about what is norm and TENORM, analyzing for norm and TENORM, and then a little bit on sample collections, which will involve sample volumes. So norm, as the name implies, is naturally occurring radioactive material. TENORM is technologically enhanced, naturally occurring radioactive material. These terms are often used interchangeably. Most people, instead of saying TENORM for technologically enhanced, they'll just say norm. So norm, the naturally occurring material, is found in your soils, groundwater, and plants, so natural environment, whereas the technologically enhanced norm, or TENORM, is created when the natural sources of radiation are concentrated by man-made processes. So examples are in the oil and gas industry, you'll have your drilling waste like produced waters, drill cuttings, and a big one is pipeline scale coming off of all the equipment and the lines. So what radioactive types, isotopes, are we looking for in norm? You have U-238 and thorium-232 naturally exist in the environment, and these decay in a series of steps until the final stable isotopes are reached. For norm, the primary isotopes of concern in waste are the uranium and thorium isotopes, radium-226 and radium-228, lead-210, and naturally occurring gamma emitters such as potassium-40. Another one that is often looked at in waters or air is radon-222. So how do we look for norm? How is it analyzed? Each isotope has a certain kinetic energy level, and the energy of the emission is what is being analyzed on the instrument. For the analyses, you'll have several different methods or technologies that can be used for the analysis. You have alpha spectroscopy, alpha scintillation, gas flow proportional counting, liquid scintillation, and gamma spectrometry. So alpha emitters are, of course, from the alpha spectroscopy and the alpha scintillation. Most of your beta emitters you're going to get from gas flow proportional counting, except for low energy beta emitters. You're going to use liquid scintillation, and that would include lead-210. And then you're going to look at your gamma spec is going to do potassium-40s In a soil, it can do radium-226 and radium-228. So more on detecting norm and what you're asking for. That's the most common question we get is someone just says, I need to have a sample analyzed for norm. Well, a project may only require a norm screen. It's what we internally have determined would be a gross alpha beta analysis, which is going to just give you the activity levels in general terms, your alpha activity and your beta activity. And then it's going to include other emissions such as potassium-40 through a gamma scan. And this only utilizes the two methods of gas flow proportional counting and the gamma spec. And this is a relatively inexpensive way to begin testing for norm because you only need the two tests. However, some people need a full characterization of norm, or based on the norm screen results, they will do a further in-depth study of specific isotopes, which is going to include your uranium and thorium isotopes, radium-226, radium-228, potassium-40, or lead-210. And a full characterization uses all or most of those methods or technologies that I showed on the previous slide. So that can be very involved, longer turnaround times, and a bit more expense for the client to do a full norm characterization. So what's really going on when you're analyzing for norm? We use specialized preps that deal with precipitations, specialized resins, and distillations to isolate the isotope of concern. Specialized resins is usually used in just the alpha spec analysis for thorium and uranium. A side note is to think of when we give pricing for isotopic analyses, these resins are quite expensive, so you're going to see a little bit higher cost when you're doing the specific isotopes of uranium and thorium. Another thing to consider when analyzing for norm is they aren't always direct analysis of an isotope. Some of the testing, the daughter products of the isotope of interest is actually what is being analyzed. And then the daughter product of the isotope of concern, those results are used to calculate back to the isotope of concern. So therefore, an ingrowth or decay period is used to allow isotopes to come to equilibrium. And these decay or ingrowth rates are based on a known half-life of the isotope, which is used in the calculations to provide a result. A good example of ingrowth periods and decay periods is used in radium-226, because radium-226 is unique in that you can use several methods to, depending on the matrix, to approach getting your radium-226 result. So if you're doing radium-226 for a soil sample using gamma spec, it requires a 21-day ingrowth period to allow for the ingrowth of the lead and bismuth 214, which are analyzed and then used to calculate the radium-226 result. When you're doing radium-226 mostly in a water, by gas flow proportional counting, it requires a 14-day period to allow for short-lived isotopes of radium to decay away so that you're looking at the radium-226. To do a water, usually we're going to use alpha scintillation method, and that requires a 7-day ingrowth period to allow for the equilibration of radon-222, which is what is detected by the instrument, and then that result is used to calculate back to the radium-226. So for a lot of these radioisotopes, because of these ingrowth and decay periods, and special preps and chemical separations, turnaround times are longer for radiochemical results than what you see in your standard stable chemistry analyses. I'm going to talk just a second about disposal of NORM material, because that's most common in waste in oil and gas industry, which we do a lot of work with operators here in Colorado. Is just a side note to keep in mind is that if it's for disposal, most of your standard record characterization tests are going to be required. And, you know, that involves your toxic characteristic leaching procedure tests for metals or volatiles or herbicides, pesticides, ignitability and reactivity. But if you're doing also, if your landfill has a specific allowance for radioactivity, you might have to do some NORM tests. If a sample is found to be radioactive and has PCBs above allowable levels for TSCA disposal, then there is typically no waste stream for a laboratory to dispose of these samples. So the process waste and/or sample remainders are often returned to the client. This involves additional expenses on the client end or the laboratory end to return samples back appropriately. This isn't always the case. You know, if you're doing drinking water monitoring and things like that, that's something you're not going to have to worry about. So collecting samples for NORM analysis. In general, a water sample is going to require 1 to 2 liters of sample, nitric preserved in a poly bottle. There are a few exceptions for this. In produced waters, again, from the oil and gas industry, limited aliquots or reduced aliquots are taken due to the sample matrix that provides interferences in the analysis. So we'll take, instead of a liter, we might take 50 mils. So it's good to inquire on what your sample matrix is to find out what we really need in order to meet the project objectives in regards to detection levels. So again, in general, each isotope that you're going to analyze is analyzed separately. So each isotope is going to require 1 to 2 liters of sample for waters. An exception is radon-222. Soils typically require just an 8-ounce jar. However, if your soil is a sediment or it's coming from a mud pit and it's significantly wetter than most soil samples, then we're going to ask for extra volume, because in the preparation for soils, we dry that sample down prior to the prep. The soils are reported on a dry weight basis, and we do the drying here. So if you have a lot of moisture in your sample and it starts drying down, the soil volume left over gets limited, so we ask for more. Preservation, like I mentioned before, is with nitric acid for most of the radiochemistry tests. Radon-222, when in regards to NORM, is another exception. And also, we often get samples for radiochemistry shipped on ice, but they do not need to be chilled. They do not have a temperature requirement, except for in certain cases like tritium and radon-222. So it helps save on cost and packing of shipping and stuff like that. It makes it a little bit easier to ship out samples for NORM because they do not need to be on ice. We often get holding time questions on radiochemical analyses, and there are no holding times for these tests with the exception of radon-222. And the radon, we apply an internal 4-day holding time to radon because it has a 3.98-day half-life, and it's to do with the analysis in that you can more easily meet a detection level if done within that 4 days, but it can still be analyzed after the 4 days It just is a longer count time, and your detection levels may be raised. So, like I said, this was a really short presentation. I think that's just more interesting if people have certain questions on norms, so they probably came with questions ready. But an interesting little note here is that a radium-containing ore back in the early 1900s was applied to the inside of crocks. These samples then would sit overnight with water in them, and then the radon, the radium decay product, could infuse into the water. And one company recommended drinking 6 glasses or more a day of radium water. Now, we know these days that most radioisotopes aren't going to be good to ingest or to be exposed to at certain levels. So it's just an interesting little historical fact that one of the project managers came across here, that this used to be a thing to drink this radon-infused water for, I think one of the terms was invigoration. So really that's it. And now I'll open up to questions. Thank you.
Thanks very much, Amy. I've got a couple of questions here for you already.
Okay.
All right. Okay. Okay. Not so much a question. Let me just. Okay. Okay. Not so much a question, but a clarification regarding definitions of norm versus TENORM. The TE indicates that some man-made processes enhance the norm, such as mining, milling, waste, industrial sludges, or industrial processes, wastes, and materials, where oil field materials such as drill cuttings or produced waters generally are not considered TENORM, in that there has been no industrial process that results in any enhancement. These materials are naturally occurring, not technically enhanced. Pipe scale would be considered TENORM. So thank you very much for that clarification. Here's another question. Are there industries other than oil and gas from which you commonly receive samples, landfills, mines, etc.?
Well, most of the samples that we do receive, like I said, we do a lot of oil and gas waste that are going to a landfill. There may be metal scrap recycling. A truck may go to a landfill and sets off one of the detectors at the landfill. Building demolitions, especially at national lab sites or ore mining process sites. A lot of mining tailings. And monitoring of wells that are associated with mining or oil and gas industry. You see a lot of operators that have to do quarterly or yearly monitoring of wells within a certain radius of these sites.
Right. Okay. Okay, thank you. What are the pros and cons to each method for testing radium-226 and radium-228 in produced water samples?
The gamma spec analysis for radium-226 and 228 in a water sample can be done, but it has significantly increased detection levels over using one of the other methods. So we do not recommend it for waters. It just doesn't have the sensitivity that you're going to get with either alpha scintillation or gas flow proportional counting. For produced waters, we typically do use the alpha scintillation technique. Method 903.1, people may be more familiar with it under that terminology. And that's because you are doing a chemical separation on the isotope, and it has a carrier that goes along with the analysis, a barium carrier. And carriers act like surrogates when you're doing a semi-volatile or volatile type analysis. So it helps as an additional method control. And you don't have that with gamma spec. You do get that with the alpha scintillation and again with the gas flow proportional counting. But gas flow proportional counting comes in with a little bit more assumption that after that 2-week decay period, that radium that you're getting reported as is just the 226 and doesn't have any of the lingering other 223 or 224 isotopes. So our recommendation is for produced waters or drinking waters is the alpha scintillation 903.1 method.
Okay. Thank you very much. Do we have any more questions for Amy? Okay, if not, I'd like to thank everyone for attending, and you should receive an email with a link to the presentation that you can download, and it's also available on our website under Webinar Wednesdays. So thank you very much for your attention, and thank you very much, Amy, for the presentation. Bye-bye now, everyone.